what we've got is a rational function. Would you agree with that? Everybody agrees, I hope, that that's a rational function.
I agree.
Oh, good. All right. And since that's a rational function, the first thing that we're going to look at is, do you see a very simple U substitution to use here to make this integral very easy to solve? The answer is no, you don't. Okay, great. All right, the next question is the degree of the numerator greater than or equal to the degree of the denominator? The answer
No.
is no. So we don't need to do division. If it was, we would divide it out, right? But since it's not, we don't do that. So the next thing we need to do is say, is this a special case? I guess we could have done that first. Is this just some special case that we know? And the answer to that is also no. And so then what we have to do is we have to see if there is a possibility of factoring the denominator. So is there a possibility of factoring that denominator?
Yes.
Yeah. What does it factor to? 1 over what?
Plus a times x minus a.
Plus a times x minus a. Yeah. And so then from there, we just need to figure out how to separate that out into its two fractions. So we're going to say that this fraction 1 over x plus a times x minus a is equal to something, we'll call it capital A, over x plus this little a, and then plus capital B over this x minus little a. Everybody good with that?
Yes.
Okay. And so then what was the next step that we needed to do? We had to find a
common denominator.
Yeah, we had to find a common denominator, which is just going to be this x plus a times x minus a. So we're just going to be left with a 1. And then we're going to have this capital A times what?
X minus a.
X minus a, because when we put that into the top and the bottom, we'll have that same denominator. And then a plus a b times the x plus a. Everybody good with that?
Yeah.
Or 1 equals ax minus capital A little a plus bx plus capital B little a. And how many x's do I have on the left?
A plus b. Oh, sorry. On the left.
I know sides of left and right are hard, but we have 0 x's on the left. And how many do we have on the right? Now you can tell.
A plus b.
Yeah. And then on the left-hand side, we have a constant of 1. And on the right-hand side, we have what is our constant on the other side?
BA minus a little a.
All right, B little a minus capital A little a. Good? And what does that tell us here? From the first one, it tells us that A is equal to negative B. And so we could go back in then right here. If A is negative B, we could just turn this into 1 equals capital B A plus capital B A. Or what does B equal?
One over 2a.
1 over 2a. And if B is 1 over 2a, then what is a equal to? Should be negative 1 over 2a. Right, since they're just opposites of each other. Good or no? Yes, no, maybe.
Yeah, that's cool.
All right, cool. So then we should be able to go back in and rewrite our integral. Our integral should now become an integral of negative 1 over 2a times x plus a, and then plus 1 over 2a times x minus a. Good or no? And what do they have in common? What constant do they have in common that can be factored out?
1 over 2a.
1 over 2a. And let's just do the integration. If I took the 1 over 2a out, this is just negative 1 over x plus a. So that should become negative natural log absolute value x plus a. And then this should become plus natural log absolute value x minus a plus our constant. And since I have two different natural logs in here, I have natural log absolute value x minus a minus natural log absolute value x plus a. I should be able to rewrite this as 1 over 2a times the natural log of the absolute value of x minus a, the one that's positive, over x plus a, all plus our constant. Good or no?
Very cool.
Yeah, very cool. And so what we want to note then is that this is a really, no, not really common, but it's a fairly common integral that comes up when you just have this x squared minus a squared, with this simple difference of squares in the denominator. So anytime you see this nice difference of squares in the denominator, you can have this integral memorized and just turn it into 1 over 2a natural log of the rest of it. Good or no?
So if this were to be used on the AP test, we could just write that out and do it.
Yep.
Okay.
Yep. Definitely. All right, we're going to do some more of these. I think it's good for us to practice these before you suffer through. Did I put up some partial fraction ones for you to start over the break or no?
No.
No? Okay. And then you'll have lots of fun tonight with this. All right, so let's take a look at this one. X to the fourth minus blah, 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 over x cubed, blah, blah, blah. So first thing we should look at is it a simple special case that we know?
No.
No, definitely not. Is there a simple U substitution that we could use?
Unlikely.
Yeah, I mean, we'd want to get rid of that entire denominator, and then we'd need a 3x squared minus a 2x minus 1. We got nothing close to that up there. So next thing we look at is the degree of the numerator greater than or equal to the degree of the denominator?
Yes, it's great.
So if the degree of that numerator is greater than or equal to it, what do we do first?
Divide.
We divide. So we're going to do x cubed minus x squared minus x plus 1 into x to the fourth plus 0x cubed minus 2x squared plus 4x plus 1. And how many times does x cubed go into x to the fourth? How many times does x cubed go into x to the fourth?
Once.
It goes in x times, right? X cubed times x is x to the fourth. You guys have done this sort of long division before, right? Back in AIM 3 or honors pre-cal or whatever class you took.
Yeah.
Yeah, okay. All right, x cubed times x gives us this x to the fourth. So we put an x up here, multiply it all out. So x to the fourth minus x cubed minus x squared plus x. And subtract it all out. That ought to give us an x cubed, and it ought to give us a, let's see, minus 2 minus negative 1 ought to be a minus 1x squared and plus 3x, and we can drop down to 1. And then how many times does x cubed go into x cubed?
Once.
And so that leaves us with x cubed minus x squared minus x plus 1. And when we subtract, that ought to give us what? That cancels out, that cancels out. This will become a 4x, and the 1 minus the 1 cancels out. So this fraction is equivalent to x plus 1. plus 4x over our original denominator. So I'll just put that on the next page, I think. This should become an integral. What do we have? We have x plus 1, right? Plus 4x. I think it was x cubed minus x squared minus x plus 1. Is that right?
Yep.
Okay, cool. And so now we've got a piece of this, two pieces of this really that are really easy to integrate. Right? The first part is x squared over 2, and the second part is just x. And how are we going to deal with the 4x over x cubed minus x squared minus x plus 1? It's a rational function, right? So we look at it and we say, is that a special case that we just know?
Nope.
Nope. Is there a simple u substitution we can use?
Nope.
Nope. And it better not have the degree of the numerator more than the degree of the denominator, because we just divided to make that not happen anymore. So that's clearly not true, which means we need to set ourselves up for integration using partial fractions. So this is an integral of 4x over something. We need to factor out x cubed minus x squared minus x plus 1. So how do I factor that out? Yeah, factoring by grouping. So we'll take an x squared out of the first two terms, x squared times x minus 1. And if we take a minus 1 out of negative x plus 1, that ought to give us minus 1 times x minus 1, or x squared minus 1 times x minus 1. And what is x squared minus 1 factor to? We gotta finish factoring that. That should be x plus 1 and another x minus 1. So x plus 1 times x minus 1 squared. Everybody agree with that factorization there? Any issues with that? Or everyone's good? Take it by your silence. All right. So we've got x squared over 2 plus x plus. No, I shouldn't be writing that out yet. Let's we gotta actually do our partial fraction decomposition, right? So this one's a little different. How is this partial fraction decomposition different?
One of the
It did.
denominators is going to be the same.
Yeah, I think I'm not sure exactly what you said, but we've got this x minus 1 squared, right? We have a factor that's repeated, don't we? Yes, everybody sees that there's a repeated linear factor there. X minus 1 is being squared. So the correct way to do the partial fraction decomposition when you have a repeated linear factor is put the constant on the top and put your factor on the bottom. Then put the next constant on the top and put that repeated factor again, and this time it's squared. And then do your last factor, c over x plus 1. So this is how we need to break down this fraction. So if I had an x minus 1 cubed, I would have a over x minus 1 plus b over x minus 1 squared plus c over x minus 1 cubed. And then I'd have a d over x plus 1. Or let's say this had x plus 1 squared here. I'd have to add a plus d over x plus 1 squared. If I had something over x minus 1 to the 7th, I'd have a over x minus 1, b over x minus 1 squared, c over x minus 1 cubed, d over x minus 1 to the 4th, e over x minus 1 to the 5th, all the way up to whatever it is, g over x minus 1 to the 7th. And then I move on to the next one. So slightly different when we've got a repeated linear factor. Good or no?
Yeah.
Okay. So now we need to get our common denominator. That's going to leave us with 4x here. What do I need to multiply the x minus 1 by and the a by to get the same denominator? I got to multiply it by,
X minus 1, x plus 1.
right, which is the same as x squared minus 1. So we'll say a times x squared minus 1. And then b times what? Needs to be multiplied just by x plus 1. And a c that needs to be multiplied by x minus 1 squared. Everybody agree with that?
Indeed.
Okay. Cool. And probably need a new page to do all of this written out here. So we now have 4x equals, and what did we multiply that one by? First one was a times x squared minus 1, so ax squared minus a. And the second one was bx plus b. And the third one is c times this. So we'll have to distribute the x minus 1 squared out first. So that'd be cx squared minus 2cx plus c. Everybody agree with that?
Yes.
Okay. And now we just need to solve for a, b, and c by setting up our system of equations. So how many x squareds do we have on the left?
0.
0. So 0 should be a plus c. And how many x's? We have 4 x's. So 4 ought to be b minus 2c. And we have a constant of 0 on the left. And so that should be negative a plus b plus c. Good or no?
Yeah, that's
Okay. And then probably take the a equals negative c here, right? Maybe do that. A is equal to negative c. And if a is negative c, and what about this one? B is equal to 2c plus 4. I could replace the a and the b here to figure out what c is. You guys agree with that? Negative a is just a c, and then b is 2c plus 4 plus another c. So what does c end up being?
negative 1.
C is negative 1. And if c is negative 1, what is a?
1.
1. And what is b if c is negative 1?
2.
Should be 2. So we've got our 3 values there. Easy enough or no? So what does our integral now become? We already had an x squared over 2, right? And we had an x. And so now we've got our integral of, I have to go back and look here. A was 1, right? So 1 over x minus 1. And b was 2, so 2 over x minus 1 squared. And c was negative 1, so negative 1 over x plus 1. So we'll say minus 1 over x plus 1. Good or no?
Yes.
Great. All right. So now this should come out pretty easily. We've got x squared over 2 plus x plus the natural log of the absolute value of x minus 1. How do we do this one? 2 over x minus 1 squared.
U sub.
U sub, u is x minus 1 and du is dx. So really I can just sort of make this 2u to the negative 2. So I'll go up to negative 1 and divide by negative 1. So that should just become minus 2 x minus 1 to the negative 1, or minus 2 over x minus 1. And then last, so we've got minus natural log absolute value of x plus 1 plus our constant. And if you want to, you can take the natural log absolute value x plus 1 and the x minus 1 and put it together as 1, or you can leave them as they are. But does that make sense? Everybody okay with that?
Yes. Fun.
Great. All right. Let's do another one. One over x squared plus a squared. Once again, this is a rational function, yeah? So the first thing we do when we have a rational function is we say, is this just a special case? Is this just a special case that we know?
No.
Nope, I don't think so. Not something we've done before. Is this going to have a simple U substitution? I don't see a simple U substitution. Okay. Is the degree of the numerator more than the degree of the denominator?
No.
No. Okay. So then we have to do partial fraction decomposition. So how do I simplify down x squared plus a squared, factoring it? You can't, right? So this is one single fraction that I can't turn into multiple fractions to integrate more easily. So we're sort of at an impasse here. We've got a problem. All 4 of the things we've done before don't work. So we've got to think back to some other stuff. What else can we do with this? Potentially. Yeah, good. So Derek, trig sub. Let's do a trig substitution here. What's the trig substitution for something that has x squared plus a squared? Normally they worked really nicely in a square root, right? But this one doesn't have a square root, so we maybe didn't initially think of that. So what should we do? What should we let x be using that inverse trig stuff?
A tangent theta.
It should be a tangent theta, which will tell us that dx is a secant squared theta d theta. And so we should be able to go in and call this an integral of a secant squared theta d theta over a squared tangent squared theta plus a squared. And what can we then do with that?
Factor out the a squared.
Factor out the a squared, which is going to leave me with an a over an a squared, or just a 1 over a that I can put in front of my integral. And I'll have a secant squared theta d theta. And in the denominator, I'm going to have a tangent squared theta plus 1, which is
Secant squared theta.
secant squared theta. So effectively, what we really got here is 1 over a times the integral of d theta. Well, what's the integral of d theta?
Theta.
Theta plus our constant. And so what's theta?
Inverse tangent of x over a.
Exactly. Theta is inverse tangent of x over a. So this is 1 over a inverse tangent x over a plus a constant. And now this is a good special case that we're going to want to have memorized and know and be able to utilize. So if we have a sum of two squares, right, x squared plus a squared in the denominator, then we should be able to turn that into 1 over a inverse tangent x over a plus a constant. Good or no?
So for the one that we did previously, where it was the integral of 1 over x squared minus a squared, we did partial fraction decomposition. Might it have been easier to do a trig sub with secant?
We could have tried that, and I think it. Let's see if we've done. Where was it? Somewhere way back here. This one, right?
Yeah.
If you've done secant, let me think about that for just a second. I feel like that wouldn't, I don't know, I was trying to do it in my head real quick. I feel like it wouldn't have come out.
Because you would get secant tangent over secant squared.
Yeah, which shouldn't be so bad actually. That's what I got, is I just did this tangent over secant, which is just sine. And that should just give you negative cosine.
But you still have the minus a squared.
Yeah, so that would have worked out fine. It would have ended up giving you an integral of cosecant, which we didn't we never learned the integral of cosecant, but it's very similar to the integral of secant that we got by doing secant plus tangent, multiplying by secant plus tangent. So yeah, you could have done that one using the trig substitution also. And you would have come out to be the exact same thing.
Okay.
Yep. But now that you know them, just use the things that you have memorized, hopefully. But yeah, either way would have worked. Good question. All right, everybody good or no? Okay. All right, let's give another one a try here. So we're going to integrate 2x squared minus x plus 4 over x cubed plus 4x. Once again, a rational function. What's the first thing we ask ourselves with the rational function?
It's not a special case.
Yeah, not a special case. Simple U sub?
No.
No. Degree of numerator more than or equal to degree of denominator?
No.
Nope. So partial fractions. Let's factor the denominator. What is the denominator factor? 2. Should be able to take out an x, right? X times x squared plus 4. Good or no? Yeah? Okay. And so now, as we separate this out to do our partial fractions, this one is a little bit different because we can't factor x squared plus 4 any further. So this time, instead of having a bunch of linear factors, we have a linear factor and we have an irreducible quadratic factor. So if you're trying to do partial fractions with an irreducible quadratic factor and some linear factors, just do the linear factors first, a over x. And then your irreducible quadratic factor, instead of getting just a constant up here, is going to get a linear piece in the top. It's going to get an EX plus C. Okay. So anytime you have an irreducible quadratic, you want to put up BX plus C or AX plus B or EX plus F or what have you up there in the numerator for it. So always 1 degree less. If you had an irreducible cubic, you'd have to put up BX squared plus CX plus D in the numerator. Good or no? Okay. So what do I need to multiply by? I need to multiply by x squared plus 4 to the first one and x to the second one, right? So a times x squared plus 4 plus bx plus c times x. And that gives us 2x squared minus x plus 4 is ax squared plus 4a plus bx squared plus cx. Everybody following along and good with that?
Yes.
Cool. All right. So how many x squareds do we have? We have 2 x squareds is equal to a plus b x squareds. And we have -1 x's should be equal to c, right? That's all we've got, cx's, right? And we've also got 4a ought to be equal to just 4. So we've already got 2 of them. A is 1 and c is -1. If a is 1, what is b?
Also 1.
Also 1. And so we should be able to go in then and write out our new integral. So this should become an integral of 1 over x plus, it was bx plus c. C was -1, right? And b was 1. So x minus 1 over x squared plus 4 dx. Good or no?
Yeah.
Okay. First one is easy, right? Natural log absolute value x. But what about the second one? X minus 1 over x squared plus 4. Another rational function, right? And if it was just 1 over x squared plus 4, it'd be easy because we just learned the rule for that, but it's not. It's also got an x minus 1. So any thoughts on how we can deal with that?
We could do a U sub.
Okay, we could do a u sub. So u would be x squared plus 4 and du would be 2x, right?
Yeah.
That's going to cause an issue though, because we don't just have a 2x up there. We've got an x minus 1. So if I multiply it by 2, we then have a 2x minus 2. But then that minus 2 is still a problem. I don't have 2x dx, right? I have 2x minus 2 dx. There's a way around that, but there's an easier way around it by not using the u substitution at this exact moment.
We separate it and then do a trig sub.
Okay, yeah, so we're gonna, the first half of what you said is right, and then there's gonna be an easier way than the trig sub. But yeah, we're gonna separate this into an integral of x over x squared plus 4 dx minus an integral of 1 over x squared plus 4 dx. So if we look at each of these separately, first this 1 over x squared plus 4, now that one looks just like the one we did previously with x squared plus a squared. We should just go to use the formula for that. What about this one? We could do a trig sub, but before we do the inverse trig sub, we always want to think about, is there an easier way? Is there a nice simple u sub that we can use? And so now a u sub of x squared plus 4 makes sense because du would be 2x dx. So if I put the 2 and the 1/2 in, now that one becomes a very easy integral. Everybody good with that?
Yes.
Any questions there? basically we're done with this one. We got natural log absolute value x plus 1/2, and then this became du over u, which is just natural log absolute value of u, which x squared plus 4 is always positive, so the absolute value is not necessary, but oh well. And then minus, and what does this one become? What's a for this? A is 2. So this is minus 1 over 2 times the inverse tangent of what? X over a plus our constant. Just from the formula we previously had. Good or not good?
Very cool.
Very cool. I agree. Very cool. All right. Are we ready to move on? Everybody feels all right about that so far? All right, let's see what we can do with this one. What should we do first? Anybody, what should we do first?
Divide first.
All right, we gotta divide first. There's no u sub, there's no special case. Degree of numerator is equal to degree of denominator, so we'll divide first. So that should be our 4x squared minus 4x plus 3 into our 4x squared minus 3x plus 2. 4x squared goes into 4x squared once. So really it just ends up like this. -3 minus -4 is just x, and 2 minus 3 is 1. -1. So this becomes an integral of 1 plus x minus 1 over 4x squared minus 4x plus 3 dx. So far good?
Yes.
All right. Any thoughts on what to do now? Obviously, the integral of 1 is just x, right? And I don't think we just know the integral of x minus 1 over 4x squared minus 4x plus 3. So let's think about what we could do. It's a rational function. So we think special case or u sub first. We see a special case or a u sub.
No.
No, unfortunately not. Okay. Degree of numerator is not more than or equal to the degree of the denominator, so we can't just divide. And then we would think next about partial fractions. Can we factor 4x squared minus 4x plus 3 into a couple of linear pieces?
No.
No, that should be a quick and easy no, because if you try to look at the discriminant of this, right, b squared minus 4ac is negative. So this doesn't factor. So we're not going to be able to do a partial fraction decomposition here either. So we got to come up with something else. Anybody have a good idea of what that something else might be? A lot of times it's nice to have a perfect square in the denominator if possible is, we know that 4x squared minus 4x plus 3 doesn't factor, but is there a perfect square trinomial within that with the 4x squared minus the 4x plus something else? Four x squared minus 4x plus what gives you a perfect square?
One.
Yeah, plus 1, right? And I still have a plus 2 left there. So if I wrote it like that and then called this x plus the integral of x minus 1 over, what is that perfect square? It's 2x minus 1, right? If I did that, would that help us, you think? The answer is yes. Why is that? Why is that a yes? Because if this was no longer 2x minus 1, if that was just u squared plus 2, then that is an irreducible sum of two squares in the denominator, right? U squared plus root 2 squared, and we should be able to use that along with this special case from way back, I've gone too far, from right here. Yeah. So could I let u equal 2x minus 1? What would du be? Should be 2 dx. So that would give us x plus the integral of, and we'd have to put in a 1/2, and then we would have a 2 dx. So we'll put 2 times our x minus 1 times our dx over 2x minus 1 squared plus 2. Everybody agree with that so far? Yes, no, maybe?
Yeah, that's all true.
Okay. All right, so then what can I do with this? I can turn the 2 dx into a du, and I can turn the 2x minus 1 squared into a u squared, but I'm still going to have an x up there, right? And how am I going to deal with that x? I need to figure out what x is. So how do I figure out what x is?
U plus 1 over 2.
Right, x is equal to u plus 1 over 2. So I should then be able to turn this. Hopefully I'm remembering everything that we just had. We had an x, so we had a 1/2 in front of our integral. We had an x minus 1, right? So that should be u plus 1 over 2, and then minus 1 all over, and then that should have become a u squared plus 2 du. Yeah? Everybody agree with that?
Yeah.
Okay. Now what?
Find a common denominator for the numerator.
All right, that sounds like a good plan. So the common denominator for a numerator is just going to be 2, right? So 2 over 2. And if I take this over 2 and drop it to the denominator, I could just pull it out, right? So what does that give us? It gives us x plus, instead of a 1/2, if we pull another 1/2 out, that should be x plus a 4th. times an integral of u plus 1 minus 2, which is u minus 1, over u squared plus 2 du. Everybody good with that?
Yeah.
Okay. And how will we deal with this?
Partial fraction decomposition.
That'd be a good idea, except that u squared plus 2 doesn't factor, does it?
Can't we split it
Separate
into two?
Yeah, we're just going to separate it into 2. We can only do partial fractions if this denominator actually factors, so it doesn't. So we got x plus 1/4 times the integral of u over u squared plus 2 du minus 1 over u squared plus 2 du. Oops. There we go. Need my 1/4 on both those. Everybody good there?
Yeah.
All right. How do I deal with the first one?
U sub.
The u sub, so can't do a u, we can do a v. Let's say v equals u squared plus 2. So dv would be 2u du, so we'd have to put in a 2 and a 1/2 there. So we're going to get x plus 1/8 natural log absolute value u squared plus 2. And then what about this one? That one's just the special case that we worked with before. So this should be minus 1/4 times what goes out in front. Should be 1 over the square root of 2 times the inverse tangent of u over the square root of 2, all plus our constant. Good or no?
Yeah.
All right. And if we go back to turning u into 2x minus 1, I think that's what u was, right? Should have 1/8 natural log of 2x minus 1 squared, which would be 4x squared minus 4x plus 1 plus the 2. So natural log absolute value of 4x squared minus 4x plus 3 minus 1 over 4 root 2 inverse tangent of 2x minus 1 over root 2 plus our constant. Good or no?
Pretty gnarly.
Yeah. So what you'll probably note is that there are a lot of different techniques for these rational function integrals. Sometimes we need to separate into multiple integrals. Sometimes we need to use these special cases. Sometimes we need to use partial fraction decomposition. Sometimes you got to do long division. Sometimes a simple u substitution works. There's a lot going on. And so I can't just tell you, hey, listen, every time you see this, do this, because every problem is very different. So you have to just sort of recognize the different techniques and start to sort of understand, all right, when I come across something that's, an irreducible quadratic in the denominator with a linear piece in the numerator, I'm going to have to separate that into 2 different integrals and deal with each one separately. Those kinds of things. You kind of got to, the more you work with it, the more you're going to just sort of see what needs to happen. Does that make sense? Yeah, we see there's a lot of techniques and we can deal with them.
Yeah.
All right, with any luck, we're going to get through a couple more here today, and then I'd like to get through at least one more, maybe 2 more. Let's see. We got 27, right? We got a little bit of time still.
Yeah, 14 minutes.
Perfect. All right, so 1 minus x plus 2x squared minus x cubed over x times x squared plus 1 squared. First off, no U substitution, no special case. Degree of numerator is less than the degree of the denominator. So partial fraction decomposition is our best bet since this has already been factored in the denominator for us. Good? Everybody good with that?
Yep.
So I'm going to just start writing out our partial fractions. 1 minus x plus 2x squared minus x cubed over all of this x times x squared plus 1 squared needs to equal a over our linear piece. And then we have an irreducible quadratic, x squared plus 1, that's being squared. So just like we did when we had a linear piece that was being squared, we're going to have to do the same thing. We're going to do the bx plus c, the linear piece, over x squared plus 1, plus dx plus e over that quadratic squared. And if I had a cubed on that, x squared plus 1 cubed instead, we'd have to have fx plus g over x squared plus 1 cubed. Does that make sense?
Yes.
All right, cool. So now we'll go through and we'll simplify it all out and see what we get. So we're going to have 1 minus x plus 2x squared minus x cubed is going to be a times x squared plus 1 squared to get a common denominator there. And then bx plus c is going to get multiplied by x and x squared plus 1. And dx plus e is just going to get multiplied by x. Good or no? Great. All right. X squared plus 1 squared is going to start off with an x to the 4th. So ax to the 4th, and then it's going to have a 2x squared, so 2ax squared, and then plus 2a. This will be bx squared times x squared. That'll be bx to the 4th. This will be bx squared times 1, so that'll be plus bx squared. We're going to have cx cubed, and we're going to have cx. And then we're going to have dx squared. They agree with all of my distributing there?
Yes.
Great. And it looks like it's going to be a pretty heinous system of equations, but it's actually really not. So if I look on the left-hand side, how many x to the 4th do I have?
0.
0. And I have a plus b on the right. And how many cubes? I have -1 x cubed, and over here I just have cx cubed. So there we go. We already got c. -1 is c. We have 2x squareds, and we have 2a plus b plus d. So that's going to be the most annoying one probably. And then we've got -1x, which should be c plus e. And then we've got a constant of 1, which should be 2a, just 2a. No, there's got to be another one in there. Is there another constant in there?
No.
Oh, that shouldn't be a 2a though. I should probably
should just be
distribute
a.
things
Okay,
correctly.
good.
That should just be an a. See, when I said, is my distributing right, and you all said yes, you gotta like check and tell me it's wrong. All right, so we got a as 1 and we got c as -1. Everybody good with that?
Yeah.
All right, so if a is 1, what's b?
-1.
That's easy enough. And if c is -1, what's e?
0.
0. Okay. And let's see. Well, all we have left is to find d. So this is going to give us 2 equals 2 plus -1, or 2 minus 1 plus d. And so what does d come out to be?
1.
1. Great. All right. So now we will rewrite this all out as another integral. So we've got 1 over x. I think we had, what was the next one? Negative x minus 1. So I could take a minus 1 out of both of those. So we'll just make that minus the integral of x plus 1 over, what was it, x squared plus 1, right? And then plus x over x squared plus 1 squared dx. Everybody good with that integral?
Yes.
All right. So what do we get? Natural log absolute value x. What about this one? X over x squared plus 1, and then minus an integral of 1 over x squared plus 1. And what about this last one? I just split that one into 2, right? What about the x over x squared plus 1 squared?
You can do a u sub.
We'll let u equal x squared plus 1. So du is 2x dx. So we'll put in plus 1/2 the integral of 2x dx over x squared plus 1 squared. Everybody good with that? And how am I going to deal with x over x squared plus 1? Same thing, right? U is going to be x squared plus 1, so I'm going to get 2 and a 1/2 there also. You all agree with that?
Yep.
All right, so we end up with natural log absolute value x minus 1/2 natural log absolute value of u minus, what's the integral of the 1 over x squared plus 1? That should just be inverse tangent x. And then this last one, this is u to the -2, so that should just become minus 1 over u. So minus 1 over 2 times x squared plus 1, because we had the 1/2 out in front, plus our constant. You guys feel like you could do this on your own without me working through every problem with you?
After some practice.
After some practice. All right. Well, we have just enough time, I think, for you guys to give one of these a shot on your own. Yeah?
Yep, let's do it.
All right, ready, go. So what's the first thing you did?
Not
U
a
sub.
Yeah. You looked at it and you said, oh, that denominator is x cubed plus 3x. Let's let u be that. And then du will be 3x squared plus 3. And all I got to do is put in a 3 in the numerator and a 1/3 on the outside. And I've got 1/3 the integral of du over u, or 1/3 natural log absolute value x cubed plus 3x plus our constant. Wasn't that nice? Yeah. Some of you probably went through and did partial fraction decomposition.
Perhaps.
Yeah, that probably took longer. So always check for that nice, simple, easy U substitution. Yeah? Yeah. If you'd gone through and did the partial fraction decomposition, that was you, a truth that said you did, right?
Yeah.
Did you finish?
No, because you said that I was almost finishing, and then you said U substitution, and then I
banged my head against a wall, so that was fun.
Ah, fun. Yeah, that's exciting. I would recommend not doing that. But yeah, my point is, don't do a U substitution if you don't, or sorry, don't do a partial fraction decomposition if you don't have to. Look for the simple U sub, look for the other stuff. And if you can use those, use them. If you can't, then go through and do partial fraction decomposition as a last resort. Cool. Excellent. We're gonna stop there.